Hey there, we're doing Facebook Hacker Cup qualification round. Looks like there are 3 problems, so let's get started. Okay, so 2 problems that have 2 parts. Let's just go to A. String S, case letters, consistent. If all the letters are the same, oh, okay. No type of replacement is given twice. Okay, so I should solve A2, it'll solve A1 automatically. Okay, so let's see. Yeah, I think so. The string S, let's read S, and then we're going to make the changes. It's either build changes or read changes. Read changes, maybe second version. Yeah, okay. So, we also have constant alphabet is 26. If build changes, then we're going to use is val. Oh, actually, I should do this. Yeah, okay, so then we're also going to make a set of the distances, or rather a 2D array of the distances. So as long as one is valid, one is not, then their distance is going to be 1. In this case, and now we're going to do void partial. So we're going to change this one to I, and we're going to change this one to J. This is the shortest path algorithm. And now that we have that, we know we want to make everything equal, so let's just iterate over what we want to make everything into. And yeah, we're just going to go through every character in S. It's going to be distance from that to C. And then it's just as best as infinity, then it's best, otherwise you can -1. Okay, so I think so we want this actually. And so here we want build changes. Oh, sorry, this one we want build changes. Okay, that looks like it's not right. Oh, of course, we also need to do this. And then I think we're good. 2, 0, 3. Okay, so let's do this. Consistency, let's do that. No. Okay. Output. Why is this a zip file? Oh no, I should have read this earlier. Okay, let's see. 7, do I have 7Z? I do have 7Z. Okay, cool. Oh, I should move, not. Okay, so 7ZE. Enter the password, okay. And txt or this is output and this is source code. And we submitted. Cool. School board. And let's start testing this one. So instead of build changes, we're going to do read changes. Okay, cool. That's not a problem. This is the problem. 2 and yep, that looks good. Let's do it. Move. And validation output. Looks good. CP. Password. And we're going to upload this. This makes sense, but this makes it a lot of steps now. Okay, so since there are 2 penalties you can get for C, it might be worth doing that instead, unless B is particularly easy. No other solves here, so okay. It does seem like B should be easy to. Okay. X is the same as the number of O's. Neither player has one yet. Oh, okay, this seems very simple. So let's do it. So I don't need D, I guess. So we just have N, read N, and then we have a grid. Alright, so yeah, so we're just gonna be counting and yeah, we're gonna go if there's an O, we have to fail. Otherwise, if there's empty, we need. If need is less than best, best plus need, count as N. Plus if need equals best, count plus plus. And after that, we're going to flip everything. Or rather, we're going to like, yeah, I'm gonna flip on the axis, and if best is greater than N, then we're just gonna see out impossible. Otherwise, we're gonna see out best and count. 1, 2, 3, 6. Okay, simple enough. And let's upload validation output. Wrong answer. Really? Two, two, one. Oh, this is wrong. Oh, okay, wait a second. Oh. Okay, I didn't get a penalty for that, did I? Maybe I did. I see. So oh, this isn't that great anymore, but I guess that's okay. Since it count as just solutions at size. Yeah, I should have caught that this was actually wrong. 1 2 3 6 2 2 1 1. Okay, cool. Oh, you just same one? Alright, let's go. Alright, let's go to C. Alright, second place. This one has a K. Okay. And caves. Okay, so this is a tree. Yep. I get everything. Okay, so as long as their LCA is 1, then you can do that. If you do it K times, that's interesting. I guess N is small. Okay, let's do C1. No, that's not what I wanted. I guess I want this. This is totally necessary on Windows 15, but we'll just do it. Okay, so input looks like N, CI, and then the edges. Okay, yeah. How big are these numbers? They add up to 1 billion. I guess I can use int. Sure. Okay, so we're building, and we're also going to do a root sum. So the root sum, I guess we can do it like this. Total list, right? Root sum x is going to be cx plus x is 0, it's 0, otherwise it's root sum. Okay, and then we're just going to do Okay, that looks good. And let's do this. Okay. Cool. All right, we're in the lead. And okay, let's work on this problem. K tunnels. Okay, so if K is 0, then you have to start at 1, go back to 1. So if K is 0, you can only get in at 1. So it's 10. Yep. Somewhere. Actually, So it's like a P on node of pass, whether top node is taken or is like included, and then whether it is extendable. So these can be like a state. 0 means no top node. 1 means top node and extendable. 2 top node unextendable. I don't need all this, I just need this. I think extend doesn't need to do anything because just attach. There's actually, are there 4 states? It's like double extendable actually. Okay, let's see. Maybe I should cut this. 3, 2, 1, 0. This is value of 0. There's no top. Right, if there's no top node, oh, if you're using 0 paths, then that's like, if you're using 1 path. Okay. Is that what I want? I think that's what I want. Okay, so yeah. Do I need a combine? Maybe I don't need a combine. I'll just keep combine, whatever. 3 is going to be root dp. Maybe Maximus is helpful. Root dp no plus okay. Yeah, it can be any state. It can be no top node. It can be any states. And then the other thing is it's as extendable as, well, if you connect it, then it's if you don't combine them, if you want to combine them, then you get one through your path, yes. Oh, that's bad. This is if you combine. Now, so it has to be extendable. So it has to be at least one. This also has to be extendable, so this has to be at least one. We're removing a path this way, and we're making this extendable. I think that's what we're going for. And what happened? Oh, I didn't call it like a function. Unused inf. Inf is unused. Root is unused. Oh, of course, this one is unused, yes. Okay. C21. So that is what we're looking for. I didn't build the results array. It's using, yes, okay. Okay, so we got 30, 10, 4, and 4. Okay, so here we got 4. So 2, 1. 2, 1, 4. Okay, so this one, we're getting 4. How are we getting 4? Actually, I think just do this. So 2, 4, 3 should all be like this. Whoa. Oh, it's not quite. Right, and this is just going to print the sum of everything. Right, I can use K. Okay. Now 18 instead of 19. What was kind of a doozy? Okay. I want to debug this. Have we got it yet? So 3 means there's no top node. Oh, I need the top node also. Oh, this is really not what I want, actually. Or at least if I do, we're going to get maximum get answer. Oh, wait. Okay, that just, if it's 0, how do we deal with that? Oh, these should be negative infinity, yeah. I do need a negative infinity. I have no pass, so we can have this. Yeah, okay, that makes sense. 16, 50, 65. Right, I think we should draw this case. Which connects to 5, which connects to 2, 3, and 4. And 6 connects to 3. 1 connects to 5. 2, 3. Okay, and 2. So we can just get everything. Oh, I'm not allowing 11 plus 8 should be, yeah, it should be 19 because you can't get everything. So I'm not allowing. Oh, okay, so this transition isn't working. Yeah, so it's like if we don't connect, we don't care what the child does. Now we want to connect, and yeah, oh wow, this is tricky. Okay, so it's actually, if There's, you know, you can do anything. If the top is unextendable and the child is extendable, you can just go through without any add-on. That can give you the one state. Let's give you one state, gives you one state. Root is extendable by 1. This gives you the best thing to do is just to do -1, yeah. If the root is just extendable, if the child's not extendable, there's no point. Zero, one, so like about 0. If this is the case, okay, so yeah, basically ours is so we're still 0. But we also get a this becomes 1. This becomes 1. And root dp 0 plus oh wow. Okay, let's try. Okay. Oh, that's not what I wanted. Yes. All right. Okay, submitted. Validation, this input. This looks reasonable. I think Jahan has 3 or 4 minutes to get me. Anyway, so I don't want to submit again. I think we're fine. Let's just check this again. So this is the validation, this is the actual. They look pretty different. Okay, cool. Are there any really large files that I don't want to save? No, everything's actually pretty small, I don't mind. In comparison, yeah. So yeah, I'll just save everything. Let's push it. Okay. And now I'll go ahead and I'll talk about the ideas for the solutions. I'm just going to go briefly over these. So let's start with problem A. So in problem A, we want to make all of the, we've got a string S with a bunch of characters, has most 100 characters and they're all uppercase English letters. And we want to make the string all equal. So every character should be the same. And the only thing we can do is we have an operation where we can take a vowel and replace it with any consonant, or we can take a consonant and we can replace it with any vowel. And only A, E, I, O, U are vowels here, so there's no weird exception around Y. And we want to know the smallest number of operations it needs, it'll take to get us to a string of all the same character. So one example is for ABC, we can just take B, replace it with A, and take C and also replace it with A, because B and C are both consonants and A is a vowel. And then, yeah, you can also go the other way. I don't know if there are specifically examples going the other way, but anyway, this is A1. And then there's also problem A2, which is related. But instead of vowels and consonants, there's a list of K types of replacements you can make, where you can replace the letter AI with the letter BI. So for example, in this case, we can replace B with A, and we can replace C with A. And so now that we have this list, we need to figure out what's the minimum number of operations to make the string all the same character. So basically, I'm just going to talk about how to do A2. A1 is, well, I guess A1 is simpler. For A1, you just pick the character that you want, and it's pretty easy to figure out how many steps you need to change that character. So let's say you want A. Well, if you have a consonant and you want to change it to A, it just takes one step. If you have an A, obviously that's 0 steps because you're done. And the tricky thing is if you have a vowel other than A, it actually takes 2 steps because you have to go to a consonant and then you have to go back to A. The way that I solve both A1 and A2 is I basically just solved A2, and you can kind of plug in the definition of A1 into A2. So, you can make an instance of the problem A2 where you have this list of K replacements consisting of all of the vowel to consonant pairs and then all of the consonant to vowel pairs. Okay, so how do we solve it for this general case where we have K replacements? Well, this is actually essentially a graph problem in disguise. It's a shortest path problem. You have a graph on 26 nodes, which are the 26 different letters, and each of these K replacements is just an edge. It means that there's an edge from AI to BI with a cost of 1. So once we know that, then we're just going to run a shortest path algorithm. So I used Floyd-Warshall, which is the easiest algorithm to code. It's just a triple for loop, as you can see here. And yeah, for A1 I use this build changes, which does the vowel to consonant distances. For A2 I actually read the changes from the input, and you can see you just set the distance from, this is AI and this is BI, and you set that distance to 1. And then you run Floyd-Warshall here. And this will basically drill down on the shortest paths from anything to anything else. So, for example, if A to B is 1, and B to C is 1, and C to D is 1, then this will figure out that A to D costs you 3. Okay, and then after that, very simple, we just go through and we check for each of the 26 characters, what does it cost to get everything to that character? And that's just the distance from what it starts from to C, which is what we're looking for. Take the minimum of all those and then output that. And then make sure to handle the -1 case when it's not possible. That only applies to A2, but it won't cause any problems for A1. Okay, so that's problem A. Let me check the scoreboard again. It'll take a bit to load. Okay, so nice. Okay, looks like Jahan did finish C2, but 6 minutes after me, and so I'm 3 minutes ahead on penalty. So as long as I pass everything, I am in first place here. So nice. Anyway, let's talk about problem B. So problem B, you're playing this weird version of tic-tac-toe where it's an n by n grid instead of a 3 by 3, and there's also no diagonal win. You can only win with a row or a column. And basically, you're given the state of a board, and you're guaranteed that both players have made an equal number of turns, neither player has won yet, and the game is not a draw yet. And your opponent, they just left, and you can cheat and try to win. You need to know the minimum number of X's you need to place on the board. That would help you immediately win. And if it is possible, you want to know the number of different sets of cells where you could place those X's to get that minimum number of X's to add to win. And this is a little tricky because you could, I had a bug actually where it messed up this count. But yeah, basically the idea here is pretty simple. You just have, you have n rows where you can win, and you have n columns where you can win. And let's say we pick a specific row where we want to win. Let's say we pick this row. Well, now we know we need to fill out 2 X's to get the all X's on this row. And yeah, so it will cost us 2 operations, and it does work. There are other cases, for example, this row will never work because there's already an O in the row. So as long as there's no O in the row or column, we can win with that, and that gives us one option. So if we just try every row and every column, we can figure out pretty easily first of all, whether it's possible, and then second of all, what the minimum number of X's we need to add is. And then here comes the tricky thing, which is counting the number of ways. So they have some tricky cases here where basically, for example, this row, it takes 1 X to win. And then if you look at this column, I can't highlight it here, but I can zoom in a little bit. If you look at this column from this X down, it also only takes 1 X to win. So you might end up outputting that the minimum is 1, and there are 2 ways to do it, right? But these are actually the same way because both of them involve just filling in this single cell. So in terms of the code, what I did is, yeah, so here's my best. This is the minimum number. I did this clever thing where I do this whole thing 2 iterations, and then in between iterations, I flip the grid, so rows become columns and columns become rows. It became a little bit annoying here when trying to deduplicate the solutions. But basically the way that I make sure I'm not double counting these is that each time I find a solution, I make a list of the cells that you need in order to build up that solution. So for example, well, in this case, if it's a row, we're just going to make a list of r times n plus c, which converts a row and column to a single number. The annoying thing here is that on the second iteration, we need to use c times n plus r because of how we flipped it. And then, yeah, we're just finding the minimum that we need. And if we just hit another solution that is equal to the best, we add that to our list of solutions. Yeah, and then in the end, we just need to remove duplicates. And so C++ has some handy built-in functions to do this. Specifically, unique does a really good job of this. And so, yeah, so then we can just, if we didn't find anything, we print impossible. Otherwise, we print our best and the number of different solutions we found. And yeah, this is important to actually deduplicate the solutions because otherwise you'll end up double counting this because you won't realize that they use the same cell. And I guess in retrospect, there's an easier way to do this because the only way that 2 solutions could repeat the same cells is if, so two different rows cannot repeat the same cells. That's not possible. It has to be a row and a column. And the only way that can happen is if it's the single one cell that they share. So you only have this counting issue if the answer is 1, actually. Yeah, same example here. So I guess I could have made this a simpler approach here rather than the way that I did it exactly. But this is good enough and would solve kind of a more general problem that you don't actually need to handle here. Okay, and then problem C. So basically, in this problem, you've got a tree, and you've got ore in each of the nodes, but each of the tunnels is, how do they describe it? It's kind of unreliable, where once you go through a tunnel, it will break, and you can't go back the other way. But what you can do is you have a rig that can drill new tunnels, and that way in C1 you have 1 opportunity to drill. In C2 you have k opportunities to drill, and k is between 0 and 50. And each time you drill you can, so for example, let's say you have 1 drill in this, you can go down to 1, go to 4, you can drill your way to 3, and then go back up to 1 and then make it out. That's just with 1 drill. With 2 drills, you can get all of these. You can go down to 1, go to 4, drill to 2, and then you could even go up to 1, go down to 3, and then drill back to 1. And with 2 drills, you can get all of the ore. So that would be 4 ore. With 1 drill, you can only get 3 of the ore. So yeah, basically the problem wants you to figure out what's the maximum amount of ore you could get if you use these limited number of drills. So for C1, when you have 1 drill, basically you're starting at 1, you're taking some path, you're drilling to some other node, and then you're going back up to 1. And you need to make sure that those 2 paths didn't share any tunnels. The only thing they share is the cave 1. So you're basically taking any 2 nodes where in the tree where their lowest common ancestor is actually cave 1, and then you can just take that entire path. So that's basically how I did C1. I have this tree code prepared in advance, build that tree code. Root sum just tells me the sum of the ore values from my node to the root. So for 4, it would be 3 because it's 1 plus 1 plus 1. Yeah, and then I just do what I described, try all pairs of nodes, and they can even be the same node because you need to handle the case when n equals 1. And if their LCA is 0, which is basically I converted all the indices from 1 base to 0 base. If they have a lowest common ancestor of cave 1, then this is an option, and you would have root sum A plus root sum B minus, make sure you don't double count the ore at cave 1. So we subtract that out. And then that gets us our answer for C1. For C2 it gets more complicated. This is a tree DP here. DP is dynamic programming. And basically there's the idea where we're doing this DP on subtrees. So for a subtree we actually have 4 different states. So there's 4 states. I'll write them out here. So for 3 means you have you haven't chosen the top node of your subtree. 2 means you have the top node and your path is extendable 2x. And then 1 and 0 are similar. Path is extendable 1x. 0 is you do have the top node. Path is unextendable. This is how we initialized with a single node. With a single node, and we also, yeah, so the main dimension is also the number of paths we're using. So the main idea is if we have k, that is the number of paths we're allowed to use. When we, for example, when we have k equals 2, what we did here is we take a path, first of all, the first path has to involve 1. So our first path might be, 4 to 1 to 3. and then our second path might be just 2. And that corresponds to going from 1 down to 4, teleporting to 2, teleporting to 3, and then going up back to 1. And by teleport, I mean dig, same thing. Okay, so that's our DP. It's the number of paths and these 4 states, like together. So it's a k by 4 array. And to initialize with a single node, if we don't use any paths, that's not possible in these 3 states, but it is possible here. So only the 3 index has value 0. Everything else is negative infinity, which means impossible. And then if we do use one path, then all of these states allow us to use that node's OR. Whereas if we don't, then it's 0. And yeah, kind of the magic is here where we're doing the transition between basically a rooted tree, and then adding a subtree to it. There's a couple different options. Basically, if you don't want to connect your root to the child, you can just take the root state and just propagate that over to the new root, and you can take the max of the child's values, child answers. And then there's 2 other kind of tricky things here. One is if we do want to combine the paths and we want to save a path that way. So let's say, the root has used 2 paths and the child has used 2 paths, but they're both extendable. We can combine them into each other and save 1 path. So instead of 4 total paths, we would have 3. That's what this is doing. Basically, they both have to be in a 1 or 2 state to be extendable, right? And then we're going to add the answers here, and then we're going to drop the k sum down by 1, and we're also going to drop the root state down by 1, because if we used one of our extendabilities, we're going to lose one of them, right? So that state will go down by 1. And then the other tricky case is if our root is in a state 0, so it's not extendable, but our child is extendable, we can take a path from our child through our root. So we would visit this root twice, we just wouldn't get the extra value from it, and that would improve our state to be 1 extendable. And so this was a tricky one that took me a while to add, but yeah, basically, yeah, so yeah, also one thing mentioned here, the caves are reinforced, and so you can visit a cave any number of times, but you only collect its OR once. So yeah, so this is all the key transition for this problem, for the states. Otherwise, it's just a pretty simple DFS, read the input. I handle k equals 0 as essentially a special case. In the case of k equals 0, you can only get the roots OR, and that's it. You can't go down anywhere. But otherwise, I do the DFS, solve the DP states, and then get the answer for k. And to get the answer, we have to make sure we don't use state 3 because we have to use the root node. And we also have to make sure that the number of paths is at most k. And so that's what we're doing here. We're just iterating these up, making sure this is only a 0, 1, or 2, and then taking the max of all of those. Okay, so that was the Hacker Cup qualification route. If you're new to the channel, I make videos on different programming contests and algorithmic problem solving. So feel free to subscribe for future videos. This is funny. Why is Snook's penalty so high? Oh, because he did both of these together. I see. Okay. Anyway, yeah, that's it for now for me. Hope to see you in the next one.